In 1927, engineer Edward Sunt sold his car to raise money to build a company that would manufacture the first small, fast-acting protective fuses. Edward had designed that first fuse to protect the electronics test equipment that he was working with and that kept failing. In just a few years, Edward's company would become Littelfuse and was building fuses to go into cars like the one he sold. And now, nearly a century later, Littelfuse is still a world leader in protective devices for all types of electric vehicles. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world. Littelfuse has been developing leading-edge electronics products for 95 years, so we are happy to welcome them back to Tech Chat. Today, we'll be chatting with Todd Phillips. Todd has a background in electrical engineering and is now the global product manager within the commercial vehicle business unit. Welcome to Tech Chat, Todd.
Thanks, Dale.
Well, it's really good to have you here, and I'm really excited for our topic today because anything where you're helping engineers how to select parts is really good for them. So I think it'll be valuable to me and to our audience.
Absolutely. And it's a really important topic that we've really excited to enter into here and having a lot of customers ask similar questions. So hopefully we can help add value to those that we haven't been able to speak to directly.
Well, that sounds good, Todd. So why don't you start us off with an introduction to DC Contactors?
Yeah, so at its most basic sense, a DC contactor is an electrically controlled switch or relay, contactor relay in certain parts of the world. Can be an interchangeable term. And it's used quite literally to switch electrical power in a circuit. Power ranges on these devices can be anywhere from, on the low side, 24 volts, which would commonly be referred to as a relay, or up to many kilovolts on the contactor side. And obviously with something that broad, with that big of a range, selecting it can be a bit of a challenge and have some nuance in it that causes questions that we see on a daily basis.
So is that kind of the rough breakdown? It's a relay if it's kind of lower voltage, lower power, and it's a contactor if it's in the higher voltage, higher power?
Exactly. That's the nomenclature that we've centered around. Certainly in some parts of the world, you'll see it used very interchangeably or very well defined. But for the most part, the two terms can be used synonymously. And we've really gone with that route to say, okay, relays, low power, DC contactors, high power stuff.
That makes sense. And obviously here you mentioned a third bolt safety. We're talking kiloamps or kilovolts. Safety is super important.
Absolutely. The last thing you want is that much power to cause an issue, especially if it's near a battery or some other source of power in the vehicle that could cause quite the fireworks.
Yeah, no, nobody wants that.
So when it comes to selecting the contactors, really there are a few key things to look at and factors as we look at what the data sheet specifications are of what I gave an example off to the right to what does that really mean for the system and how should we think about those? So often you'll hear customers ask for the current rating. Oftentimes that means on the data sheet, what is the continuous current rating or what can that contactor handle indefinitely? So from a system standpoint, that can be really important, right? How many loads of what amperage do I need to drive through this contactor and for it to allow that power to drive through without overheating or becoming a danger to itself. So that's that continuous current rating. But like most things, there's always a trade-off. A question we often get as it relates to current rating is, okay, it's a 250 amp device. Can I drive it at 300 amps or 350 amps? And for how long due to various conditions that may occur with the battery? And many data sheets, and we're included in this, we provide a current versus time chart to really help narrow in on that because it's a trade-off of those of those specifications of time versus current. So that's the first area that becomes important. The next is the coil voltage. The coil voltage oftentimes is something selectable. There's multiple options for a given contactor. And it really speaks to how much energy or how much power, what's the voltage that we're going to drive and control the relay with. So not the main power circuit, but when I need open and close it, what sort of control voltage do I have? And anywhere from one to a few options may be available there. Next up would be, what type of contactor is it? So is it normally open or normally closed? Meaning, what's the state of the relay before and after the control circuit has been activated? Another one that becomes less of an issue or a question, I should say, on DC contactors, but certainly affects all relays is the latching versus non-latching, meaning do I need to power the coil continuously, or can I pulse it with power like a latching relay? So some applications, they want to power the contactor continuously through the coil. That would be a non-latching relay because that magnetic field is continuously there to keep the relay closed. And then other applications where maybe they want to save a bit of energy, or they don't have a safety concern by the relay needing that power to keep it closed. That would be like a latching relay. And I think the best example of that would be like a retractable pen, where you click the pen and the ink gets ready for you to write, and you click it again and the ink portion of the pen retracts and you can't use it anymore. In this case, for a relay, it's you pulse the relay once and it closes the contacts. You pulse it again with energy, and it opens the contacts. That can be really beneficial for applications that are strapped for energy and they really want to conserve that extra bit of power for powering the coil. Next up, and probably equally as important to the current rating, is the max voltage rating of the contacts. So, as mentioned before, a contactor is really, it's disconnecting power, or it's meant to break a power circuit. And the voltage rating says, well, how much voltage can it safely disconnect? And like with many things, I mentioned it on current, that's a bit of a negotiation, and we'll talk about that on a later slide. But typically what you'll see is what's the maximum voltage rating for the device, and that's what we provide here. So you definitely want that to be higher than the maximum voltage rating of the system. So if you have a 450 volt battery, you definitely want a contactor that is able to disconnect at least 450 volts.
So Todd, just to make sure I'm clear, I'm more of a transistor guy from lower power. So this coil voltage would kind of be the equivalent then of a gate voltage that turns the transistor on and off. And then the voltage rating is the kind of the drain to source voltage. That's what's doing the actual work in the system. Exactly.
When it comes to polarization, actually that's on a topic for the next slide here, but really something that we get is more frequently recently on questions of, what does it mean to be a polarized relay, number one? And number two is, what if current is flowing in both directions during different situations where the contactor may be called upon to be either just remain closed or open and closed during those different conditions?
Well, I certainly don't know what polarization is in this context, Todd, so why don't you explain it to me and the rest of the audience?
As we look at this slide here, we've included a couple of visuals to help this, and they're pretty busy, so bear with us there. But what we're really looking at is two contacts in each instance. What we're showing is current flowing in two different directions based on these contacts. And so the contacts are the really dark brown, and then in relation to that, on each diagram, we've got magnets. And magnets are really utilized in high-power DC contactors to help quench the arc that occurs when opening or closing those contacts. Just like a fuse has an internal arc, and a circuit breaker does, anything that's switching power as you move those contacts away from each other, that voltage is going to jump the gap until it reaches a certain point, and then that arc will be extinguished. In a contactor, we use magnets to help not only speed up that process, but using the magnetic field, you can actually elongate or create what looks like a larger opening distance between contacts to that electrical arc with those magnetic fields. Polarization, what that really means is that when current is flowing in certain directions, that's going to, when the magnets are there, they're going to force the arc and magnetic field to extinguish in a specific direction. So polarized contacts are one in which they expect current to always flow in a specific direction. And like this diagram here on the top, we're expecting current to flow from left to right using nomenclature of, negative to positive. And the magnets are on the opposite side. And this is like the optimal location to get the best life out of the contacts. And what happens is when those contacts start to move apart, is the red arrows indicate that arc starts to occur between them, and the magnetic field forces that blowout. Sometimes you'll hear of that as a magnetic blowout is included in the relay, and that's what it's referring to, is that extinguishing. Well, now if you reverse current flow, the magnets actually cause the arcs, instead of going outwards, where you see the green arrows pointing out in the top diagram, what you see in the diagram there in the kind of middle to the right is you see that those arcs from the magnets being pulled in close to each other. So it still works, but it doesn't work as well. And if you do that too many times in a polarized relay or contactor, you can actually start to damage the relay and it becomes unreliable after a period of time. So in applications, think of like a battery application where you're driving loads from the battery, like you're powering the wheels of a vehicle from the traction battery. At other points in time, you're trying to charge that battery through that same contactor. So current would be flowing into the battery instead of out of it. And in that case, you would probably want to use an unpolarized contactor, in which case we change the position of the magnets so that it's always, regardless of the flow of current, it's always causing that arc that is created to blow away from something else. The interesting thing is that when we change the location of those magnets, it actually has an effect on the overall cycle life of the relays or the contactors. Most instances, when you've got a polarized contactor, that provides the highest number of lifetime cycles as you would ever expect. And then by going to a non-polarized one, it decreases that a little bit, but it makes it more long-term reliable for instances where you're almost guaranteed to have current flowing in either direction when the contactor is needing to open.
So if I understand correctly, in most situations, if your current is going to change direction, you're probably going to want to choose a non-polarized contact. And if your current is guaranteed to always go in one direction, you're going to want to lean toward the polarized contacts. Is that kind of the simplification of it for most cases?
Yes, exactly. And one point that I neglected there is that this really only matters when you're opening and closing the relay with a load current flowing. If there's no load current, then it's just a mechanical switching and you're not worried about that arcing that's occurring. But you summarized it very well.
Good. And the magnets, in either case, they do help during the opening and closing process. It's just how they help, I guess.
Exactly. And in all cases, they're there to extend the life of the contactor, because without them, they wouldn't last nearly as long.
Oh, that's very interesting. I wonder who first thought of using magnets to help with that.
I don't know. Somebody really smart, I suppose.
Well, Todd, so what are some other key portions of the data sheet that engineers should be looking at when selecting a DC contactor?
The other one that I alluded to earlier is, again, back to that voltage rating. So of the main contacts, this can be a bit of a negotiation, as I mentioned before. So when we look at the voltage rating, we always want to consider what's the system voltage. And when it pertains to the contactors, what are the load conditions during the opening and closing? Again, I mentioned that on the polarization. It matters there, but it also matters in this instance for the voltage rating of how much current is going to be flowing through the contactor when you're opening and closing it. And then the last one is, during the life of the application, how often is that amount of current and voltage going to be required to be open and closed by the relay, or connected or disconnected? And that's where this chart that's provided on the data sheets becomes really helpful, because you can look at, for example, this 250 amp relay. you can see that if you have a constant current, if you have no option to change the current value, your life cycles of that contactor will increase if you've got lower voltage or decrease if you've got higher voltage with 250 amps. The other thing, and what most customers do in applications, is that they decrease the amount of current flowing through the relay when the relay or contactor is set to open and close. And by doing that, they can really extend the life of the contactor. So if we look at this red line here and say, 900 volts is always going to be present. So that's our leftmost line is labeled here on the chart. If 900 volts is always present, if at worst case scenario, we've got 250 amps flowing through the contactor, that contactor through its entire life can handle that just about 20 times. However, if we decrease that current so that there's only maybe even 100 amps running through that contactor, the life is extended pretty significantly. You can see by the chart using the log scale on the left, let's see, 100, 2, 3, 4, 500 cycles of 100 amps and 900 volts is possible through the lifetime of that contactor. So you can really start to play with these numbers and using the electronics of the system, dial in what the performance is needed of the contactor. And oftentimes when customers are asking about this, it at first seems very black or white, but it definitely becomes a bit of an art and a gray area when we're looking at what's the voltage and cycle rating of the device.
Yeah, that's very interesting. I mean, you've got 5 orders of magnitude there. So that's a pretty significant difference. And I could see why for increasing the lifetime, being able to control at the system level the current before you switch is going to be very important. It's probably why so much more intelligence is going into power systems as well.
Exactly. And something we see customers all the time in applications employing that behavior, because a little less than half the current, and you don't have to shut it completely off, but you can really extend the life of those contactors. As we move from, how do we select a relay for a mythical application and all the specs that we may be needed, let's take a look at some, actual real world examples of applications where we see these types of devices used. The first example here being a general, we've got a picture of a tractor there, but it's, off-highway vehicles tend to have a similar architecture. Tractors, small excavators, forklift trucks, and I should say electric tractors. Typically, probably don't see this in the combustion engine vehicles. But what you see here in this block diagram is not only are there multiple locations where contactors are used, there's multiple locations where protection circuits and control and other devices, power distribution modules all come into play, and that a supplier or a company that kind of has a systems approach can really benefit in working together. One of the areas that we see contactors use is first and foremost, number one, there's in the junction box related to the battery. We can see them powering various loads very often, like in this case, the PTC heater that may be used to defrost the mirrors. Oftentimes, the PTC heaters can be used to make sure the electric motors are, not frozen or anything like that. They do a little preheating there and other such circuits, but the current is lower when driving those loads. So we see about a 50 amp contactor being used there as it's powered directly off of the battery. And then, number two there is the other one. This would be the main contactor. So in the example I used before in talking about a location of the battery getting charged and then discharging as well through a common main contactor, that would be that 100 amp or higher for these types of applications. Up to 200, 300, 400 amps is what we've seen in those locations. Both typically have about the same voltage rating, and then depending on the system, you'd see the similar coil ratings. But those would be the two most common locations you'd see it in an off-highway vehicle.
And I guess then from your previous discussion for the battery pack and battery management system, that contactor is probably going to be polarized because you're going to be charging that battery pack, but you're also going to be using it to drive everything. and then the junction box could probably be non-polarized. Am I remembering that correctly?
Yes, yeah, that would be definitely one way to look at that, and often what we see as well from customers. Interestingly, we do see customers using the polarized version even in that main contactor, just because of the way that they're able to control the circuitry. They're not necessarily looking at needing that contactor to open many times throughout its entire life with current flowing in either direction. It's maybe once or twice throughout its operation. So even in some cases, they do use a polarized version in that main contactor for the battery pack BMS. But just as often, we see customers using the non-polarized.
Yeah, makes sense. Engineers are always going to do their own thing, right?
That's right.
And then I see here in your table that you use both terms. They're contactor relays. So as you sell these across the globe, I suppose you got to use both terms to pick up everybody's meaning.
That's exactly right. You don't want to leave anybody out there in terminology or misunderstand what we're talking about there.
That makes sense too. And even though we're focusing on the DC contactors for today's discussion, this table shows that Littelfuse has many of the components that these people would need for these applications.
That's right. And that's, again, back to kind of the systems approach that we like to look is, it's not just focusing on one technology and trying to support on that. It's really looking at what are the problems that the entire system, especially for electric vehicles, which is newer and has a lot of variation in how the designs are approached. And I think having visibility to what's occurring in multiple areas can really be beneficial there as we look at, looking at then any individual solution.
Sure. And I was thinking even back to your data sheet earlier, you didn't talk about it, but I saw an IP67 environmental rating in that particular example data sheet. And so in this environment, that'd be really valuable. You got to protect against dust and moisture, where other applications that wouldn't be necessary.
Yeah, exactly. And definitely here, IP67 is a high, it's a requirement that comes very, very frequently. And it's mostly there because they're not placing in these applications the contactors in, say, another containment box, like a power distribution module or battery distribution unit. They place them wherever they can in some cases, which is actually a good transition to an application where they do very typically use them inside of another box. So IP67 may be nice to have, but not 100% necessary. And that's like in the heavy truck and bus applications.
So here you have in this truck and bus application, you've got higher voltages and increased currents. So is that why you need more DC contactors in these applications than you showed on the previous graph?
Exactly. So you'll have more loads coming off of that. So those are certainly there as number 4 would indicate, some of those auxiliary contactors, you'll see more of those. Some of it does have to do with how when you scale up the application, you do tend to find a unique set of contactors used in different locations. So having a contactor on the main positive and the main negative, as well as then a different charged contactor that is between the battery and the charging circuit. And what you see here in 2 and 5, between the battery and the loads. The other thing that you see here that you don't find in the other one is a pre-charge contactor. And these are really used to help in a pre-charging circuit so that when the main contactor closes, you don't get such a high spike of current emitting from the battery where it really helps dampen that a little bit. It's almost like a way of doing a soft starter without having to deal with those higher inverse currents.
Oh, that's interesting. Yeah, I was going to ask about this when I saw this line graph. So you're kind of passing some of the load through to pre-charge, like you said, and then so you kind of queue everything up and then you let the rest of it go through with the main contactor. Exactly.
And the timing is that it's not pictured here, but there is a charge capacitor that while power is flowing through that pre-charge contactor and resistor, it's essentially charging up that capacitor so that when you do open up the pre-charge relay and at the same time close the main contactor relay, that charge capacitor is built up and it helps to alleviate that inrush current.
Oh, and then that helps the cycle lifetime that you talked about on that make-break chart.
Exactly. And then, of course, looking at another application, not necessarily on the vehicle, but very much in support of vehicles. The EVSI, as it has been called, or the EV infrastructure, EV charging side. That cabinet that you would have to go plug into to get power to the battery. Again, high voltage DC, lots of electronics and a lot of things going on here that we could support. But to highlight for the contactor portion is typically you'd see two 500 amps or higher, depending on what the power level is coming out of that charger. You'd see two contactors, one on the positive circuit or one on the positive line, and then another one there on the negative line, as indicated there, kind of in the top middle part of the diagram. Other things to note, actually, so there's AC contactors also then out there on the AC side. That's an interesting one that we've seen some customers even consider a DC contactor in that location. But of course, we're happy to pour it on either as we have defined purpose and AC contactors to go out there. But that's a kind of a new and evolving one to consider some pros and cons of using a non-polarized version out there.
That's interesting. Maybe this is a better topic for a future tech chat, but at a very high level, how is an AC contactor different from a DC contactor that can support flow in both directions?
Yeah, so typically AC contactors come in multiple phases. So on the AC high power side, you're going to have three-phase circuit. The other thing, the main difference is going to be in just robustness of the relay or contactor. Again, using those terms interchangeably. In the robustness of it, because when you think about DC, it's high power all the time. You don't have that oscillating curve that crosses 0 60 times every second if it's in the US. On the AC contactor, they don't need to be as robust because they have those zero crossings where when you're opening the contactor, you get some benefit and help from that zero crossing. So they don't need to be quite as robust out there. So on the DC side, you tend to see a more robust, higher cost device because it needs to be able to handle that power, no zero crossing option, lower cost, less robust type of device on the AC side. So definitely some trade-offs there as you consider that.
And that kind of goes back to your discussion earlier where you said you can operate these devices at higher voltages, higher currents for a time. Here, the AC spends a lot of its time below its peak. So that kind of explains the lower cost and the ability to use a less robust for the same peak voltage, shall we say.
Right. Yeah. Less robust, just to be clear too, it's less robust in comparison with each other. Well, I would say probably well suited for the location where they go, right? It's not they're not undersized by any means on the AC side.
Yeah, we should be clear. They're not less robust in that regards, but just fit for the application requirements.
Exactly. So as we kind of close out the application discussion, just giving a brief overview of what we do have from a product portfolio standpoint. This is something we're really excited about, how we're expanding this. We had entered into the DC contactor market a few years ago and an offering of good products right around that 900 volt and even higher in some cases range, anywhere from 30 to 50 amps. We could hit those pre-charge relays and then even extending up to 500 amps for the higher power applications, but adding to that a much broader portfolio. And most notably, bringing in products with lower voltage rating that can be well suited for those smaller commercial vehicle applications where maybe they don't need the capability to handle 900 volts. Maybe it's only 120 volts or 60 volts or less. So getting well tuned, as we talked about in the previous slide, well tuned for the application, not oversizing things too much. But a big launch for us, and really excited about it, and just encourage some of these products are available sooner than later, as you can imagine, with a big launch and a big expansion of a product line that takes a lot of work and a lot of coordination. So some will be available sooner than others. So if something piques the interest, as you're looking at this slide here, definitely encourage you to reach out to the local Mauser branch or local sales office to get additional information and see how we can help out.
Well, Todd, that certainly makes sense. You're expanding your product line in this market because the EV growth in, it's not just automobiles anymore. It's everything, as you've got it listed here, from electric bicycle all the way up to heavy duty electric trucks. So it's a pretty broad span. And so it's not surprising that you guys at Littelfuse are planning to cover that.
Exactly. All good opportunities where we've already been working and we have customer engagement. It's just another look at it and another area that we can help support.
Now, one of the things in this table that we haven't talked about is the auxiliary contact. What is that?
Yeah, great question. So the auxiliary contact oftentimes is used as a monitoring device to say, what's the state of the relay? So a lot, especially in higher voltage applications, this gets important to know, is my relay actually open or closed? So what you're telling it to do from, how you're powering the coil and telling it to open or close the relays. But over time, or some conditions may occur, which may prevent that contactor. Oftentimes it gets prevented from opening when you expect it to. So there's actually a micro switch mechanically linked inside. It will confirm no power to the coil and the relay's open, or no power to the coil. Hey, this is still reading as a closed relay or a contactor. Need to go check something out. So they can often be used as a safety check to say, is the contactor doing what I told it to do? And that can be really important for some of those higher power applications.
Yeah, very fascinating. And again, that just gets back to how complex these systems are and how the intelligence can provide not just more performance, but more information of what's going on.
Exactly.
So Todd, for engineers who are getting started on new designs, what resources do you provide at Littelfuse?
So lots of different resources. All of them can be found either on our website or at this link here through Mauser.com. A specific landing page with drawings, data sheets, 3D models. That's a big one, as you're scoping out the battery box or the location where you want to place a device. Those can be really helpful. Installation instructions, cross-reference. If they already have something in mind, we can take a look at that number and say, well, here's the closest fit, or here's a drop-in replacement. And then, beyond that, it's the knowledge of the application notes. So some of the topics that we touched on, like polarization, getting to explain that in a little bit more detail of how does that affect the contactor, how does that affect the application. And then, trying to help simplify it, because as we talked about, there can be a lot of maybe confusion, but certainly a lot of factors to balance when looking at the selection of a device is provide selection guides. So quite literally helping customers go through that flow chart of how to get to that part and hopefully make it as simple as possible.
Well, Todd, that was really helpful. I know I certainly learned a lot. Before we close out our tech chat for today, is there anything else you'd like to share with our audience?
Just appreciate the time and look forward to hearing more about the applications. This is an area of the market that's really attracted me because of how important it is to the global environment and how exciting and nuanced and different every application can be. So I just really look forward to hearing from everybody and hearing what we can do to help out.
Well, thanks for that. Audience, you heard that. Todd and his team are ready to help you guys pick the right DC contactor for your applications. These products are available for purchase at Mouser Electronics, our sponsor for today's Tech Chat. So I'd encourage you to check out the Littelfuse products page at Mauser.com. And please join us again next time on Tech Chat, where we chat with the leading technical experts like Todd Phillips from industry-leading companies like Littelfuse, who are changing our world every day.